Good evening, everyone. Myself Karan Das from EC Department 30. This is the engine of the simulation. It takes a continuous signal X and squashes it into n bits of resolution. It calculates the total number of available discrete steps using L equal to 2 to the power n. For 3 bits you get 8 levels. For 8 bits you get 256 levels. Step size is determines the height of each stair by dividing the total voltage range Vmax minus Vmin by the number of level L. The signal is divided by the del and rounded down to assign each sample to specific integer bin from 0 to L minus 1. np.clip act as a safety limiter so that maximum value of exactly 1.0 doesn't accidentally spill into a non-existent bin. The digital signal is revealed by multiplying the indice by the step size, adding half a step del by 2 to center the value in the middle of the bin known as a mid-riser characteristics. It converts the integer indice into raw binary strings, mimicking how hardware actually transmits PCM data. You generate a 2 Hz sine wave sampled at 1000 Hz. Because the amplitude goes from -1 to 1, the theoretical signal power of a pure sine wave is exactly 0.5 or a square by 2 where a equal to 1. The code runs the quantizer for 2, 3, 4, 6, and 8 bits. For each run, it calculates the mean square error (MSE), which is the average power of the quantization noise, the gap between the smooth curve and the stairs. The mathematics of SQNR, the actual signal to quantization noise ratio, is calculated using 10 log 10 signal power by MSE. For a full-scale sine wave, the theoretical formula is SQN at least 6.0 to n plus 1.76 dB. Your code prints both values side by side. Our code prints both values side by side to prove that the theoretical perfectly matches the simulated reality. Plot 1 overlays the blocky 3-bit signal on top of the smooth original. Plot 2 plots input versus output to show the classic staircase function of a uniform quantizer. Plot 3 proves that quantization noise is roughly uniform distributed across the bins, which is a key assumption in digital signal processing (DSP math). Plot 4 visually graphs the measure SQNR against a 6.0 to n plus 1.76 formula showing a perfect linear correlation. Now we'll explain the graph. For original versus quantized waveform, n equal to 3 bits, represent the original continuous sine wave in the time domain. It has infinite possible amplitude values. Shows the red line shows the quantized signal at n equal to 3 bits. Because 2 to the power 3 equal to 8, the y-axis is sliced into exactly 8 discrete horizontal steps. The red line snaps to whichever step is closest to the black line at any given moment. Now the staircase characteristics n equal to 3 bits. The ideal linear, if we had infinite bits perfect analog, the input would equal the output perfectly, forming a clean 45-degree line. The quantization output blue solid. Blue solid. This visually defines our uniform quantizer for any given input range on the x-axis. The output is climbed to a flat step on the y-axis. The width and height of each step represent our step size delta. Then quantization error histogram n for 4 digits. The error is calculated by the subtracting the red line from the black line in a graph 1. This histogram proves that the error is strictly contained within a specific boundary, specific plus minus del by 2. It never exceeds this limit. While ideal random noise from a perfectly flat rectangular block, this histogram has peaks at the edges. This happens because our input is a sine wave, which spends more of its time flattening our at out at its maximum and minimum peak than it does crossing zero. Now, SQNR-B versus beat resolution. Uh, the green dots are actually actual data generated by our Python loop. The red dashes line in plotting using the theoretical formula SQNR equal to 6.0 to n plus 1.76. The fact that the green dot lands exactly on the red line proves the 6 dB rule. For every single bit of resolution we add it to a digital system. The signal to noise ratio improves by roughly 6 decibels, resulting in a clear sound. That's it. Thank you.